Okay. First of all, thanks for coming around. I know I'm the only thing between you and lunch, so I really appreciate you making it. Today, we're going to talk about how to build an exchange. Yeah, I know. You're like, again with the exchanges? Every Ruby conference has one of those talks by now. Build financial exchanges, that's pretty boring by now. I built 2 before breakfast already. So, hopefully we learned something, but first we have to have a speaker introduction, obviously. So, my name is Tim. We are going to skip the last name because leave it up to the Germans to confuse everybody with the umlaut in last name, right? So, what you need to know about me, I work in finance. I work at a German exchange called Börse Stuttgart. I don't have a trust fund. I'm not 6'5", and I don't have blue eyes. So that's basically it. I'm really sorry. I'm not the whole package, really. So let's start. What is an exchange? It's an exchange, a marketplace where people meet to buy and sell securities, derivatives, other instruments. You know them. Okay, now we know how Investopedia defines an exchange, a financial exchange. So, but what is it really? Maybe it's this. Back then they didn't have colors, so that's how they rolled. Nobody noticed that the suits were pretty boring. It was boring people in boring suits shouting prices at each other and swapping papers in a building. That's all there was to it. These days, you're probably more familiar with the New York Stock Exchange, big screens, prices now on televisions. Revolutionary stuff, really. But don't be fooled. These days, still people shout prices at each other. But actually, this is nothing more than a glorified TV studio at this point. The real trading, some trading still happens on these floors, but most of the trading actually happens somewhere else. And that's here. Admittedly, this is a Google data center. The financial data centers are usually not so fancy. They are really in the cost cutting. So no lights, it's darkness. So, and this is the only reason why we talk about it today, because while I have seen a trading floor from above, I wasn't on a trading floor yet. So, okay, if it's just a boring building or a data center, why go to an exchange in the first place, right? I can do that myself. I can shout prices. That's okay. Well, an exchange gives you something. The responsibility of an exchange is to match buyers and sellers fairly. One thing, among other things, is price transparency. You know what a certain thing is worth it and what people are willing to pay you for necessarily. That's one thing. And the other thing is predetermined rules. So when 2 people want to buy something at the same price, who comes first? It's generally not a good practice to have that. It's for stocks. It's really bad for business. So how are we going to do this? Well, we maintain a central list of buy and sell orders for each market. That's a mouthful, really. What does that mean? Well, let's talk about what a market is. A market can be anything. It can be a commodity, such as onions. It can be a share. It can be stocks. It can be derivatives. But they are different markets. So if you have stock A, that's a market. If you have stock B, that's a market. But they are not the same market, to be clear. And if you have a buy order, it goes into this list. If you have a sell order, it goes into the list. That's how it works. And we keep a list for each stock, derivative, onion, whatever you have. And how are we going to do that? We have to look at the heart of the exchange. They're really creative. If you know an admin interface, you know this table. It's a table. So you have a buy side, you have a sell side, and you have price and quantity in this table. So the red line differentiates between the buy side and the sell side. So how to read this? Well, let's look at the first row. We see there's a demand to buy 20 shares at a price of 8 or less. And the less is important here. Because if somebody would come around and offers you the share for 7, you would be a fool to say, no, I wanted to pay 8. I'm going to pay 8. That's a bad practice, right? You would take it for 7. So it's a limit in that sense where you're like, I would be willing to pay up to 8 at this point, not more, not less, but less, actually. And same for the sell side, actually, but there it is switched. You're like, you want to sell it for 15 or more. If somebody wants to offer you 16, you're like, yeah, I'm going to take it. I don't have a problem with taking more money. So, but to really understand how an order book works, I think we need an order. By the way, does anyone know this person? Our example order looks like this. I want to buy 20 shares for at most 12 euros. Okay. Let's look at the order book. Fun fact, it's the same as you saw previously. I was very lazy copying it over to the next slide. So we're going to insert the order. And as if somebody planned it, there is an overlap. Like you have 12 euros on the buy side and 12 euros on the sell side. And you know what that means? You can create a trade. Amazing stuff, really. So we update everything. You see, we wanted to buy 20, but the other side has 23 available. So we write the remainder, 3 on the sell side, because now we have had a trade. And we end up with this, the trade. And the trade always has 2 sides, a buy side and a sell side. And that's there. The agreed upon quantities is there, and the agreed upon price. That's basically what a trade is. Sometimes there's more information, clearing information, but that's the basic of a trade. And for those who may want to know, a real trade always has 2 sides. If there's only one side in a trade, it's not a real trade. Ask Bernie Madoff. It's not a real trade. Now we talked about the principles, we talked about the tables, riveting stuff, really. I think we need to talk about the computer part. And this is the return of the big O, as in, oh no, data structures. We have to talk about the data structures. And one thing very important for an exchange is speed, and for that matter also latency. So every common operation should be constant time. So O of n is the ideal. For less operations, we may go with something a bit slower, but generally speaking, O of n, O of 1 is the target. Okay, let's look at the data structures. We have the limit. This is the row you saw in the table. We call it a limit because, remember, we are willing to pay to this price, and it has a price and the orders that want to buy or sell at this price level. You see, it's a linked list. So if you know that from university still, it exists, it's used in real life. And we basically treat it as a queue. So usually you pop the queue from the beginning, so the first order is the one, and we append to the end. That's how it works. Okay, then we have your limit order. This is really just a plain old Ruby struct. We have an ID to identify the order at the end of the day. We have a side user ID because we want to know who entered the order in the end, and the quantity and the price. Then remember, we have the trade. Trade's always a buy and a sell side, so we have both sides in the trade. And in the end, we have the order book. The order book is a bit more complicated, actually. We have a buy side and a sell side, and they are a sorted map of some kind. So we have a mapping from the price to a limit. The limit already has a price, but we want to have this explicit mapping to have easy access. And for a sorted map, you usually use something like a B tree or a red-black tree. All the fancy data structures you heard of but never used, they are the order book. Okay, so we need to talk about the matching, right? We already did one on paper, but now we have to do it in code. Okay, very simple stuff. You get the highest buy order and you get the lowest sell order, like the highest price on the buy side and the lowest sell price. And then you have these 2 orders. Okay, and then what you're going to do is you check whether they have an overlap in some capacity. Like, is it the same price or do they overlap in some way? And then you establish the minimum quantity that can be exchanged. Remember, one person wanted to sell 23, the other wanted to sell 20, buy 20. So we can't exchange 23 because somebody is going to end up with more than they actually wanted. So we have to check for the quantity. And then we are going to create this trade object that we had. We are going to update our order book accordingly on that price level. And we're going to publish that trade. That's it. Admittedly, this is presentation code, so it's a bit shorter than the real thing, but this is the real thing. And for those that didn't know, there's a while loop in Ruby. You may have never seen it, but it exists. Okay. But the really interesting part of an exchange is the system. Because we have system requirements. We have high availability. Think about it. If you start in the morning at 7 and end at 10 in the evening, with a full trading day, you have to be up and running. And generally speaking, when huge sums of money are involved, people frown up on the fact that your exchange went down. So high availability is kind of a given. And during a trading day, you're usually hammered with requests and orders. We have auditability. Auditability is, given the sums of money, also very important, because you need to, if somebody comes around and contests the trade, you want to be sure that you can pinpoint where the order entered the system. So auditability, kind of a cool thing. And determinism. This goes also back to actually the money thing. You don't want to be the developer that's like, you know, I know it's a bug, but I couldn't reproduce it in RSpec. I'm really sorry. Didn't work out. So we have to have determinism built into the system. We can't be like, well, there was a full moon, and so a trade happened, and we didn't know why. We need to have determinism. And how are we going to do this? I think we have to lay some ground rules. Number 1, no threats. No threats. Not today, not ever. We are going to have a single while loop at the center of our exchange, and it's going to process one message after another, and then chugging along. That's how it will work. We are not going to deal with the React, with the fibers, whatever they now introduced, green threats, real threats, fake threats, none of them. No threats. And that makes it a very, very simple system if you don't have to think about deadlocks or race conditions in the end. Then we are just going to say no to I/O. What do we mean by that? For the Haskell folks in the crowd, that's the I/O monad. So, we're not going to read the date. We're not going to read random numbers. We're not going to read the system in the end. None of that. No I/O. We are going to have a system that looks like this. We have a state, we apply an event, and we get a new state. And for those that went to university and were tortured with it, that's what you call a state machine. And I know everybody has a state machine basically in their system in some capacity, but it's oftentimes just not a very well-defined one. And we want to have a well-defined state machine in the end. So, it's going to start easy with this. We have some clients, we have a WebSocket. I put a WebSocket in there so that you're more familiar with it, but oftentimes in the real world, it's a TCP socket. They exist outside of a browser. So we have a WebSocket, clients connect to it, and we put every message that we get on a message queue. And then we have this matching engine. This is the actual exchange with all the rules and the order books. And it's going to process one message by another, and then chugging along and sending it back via the message queue to the WebSocket. And with this message queue, we have established full ordering of the events, because they are all going to be in sequence in this message queue, and we process. Okay, so we solved the determinism thing really, because if we know how the message queue looked, we can replay everything. Okay. But I think we now need to talk about the elephant in the room. Where's the database? Where is this elephant? We all know him, her, we don't know the pronouns, but where's the database? Well, we are probably not going to have one. Not a real one, at least. Not a relational one. I see scared faces. Because databases come with a lot of stuff, and oftentimes it's very useful stuff, like ACID compliance. MongoDB never knew how that worked. So we have ACID compliance in our database. We have transaction safety. We have isolation, all the good things. But that comes at a cost, and that cost is speed and latency. So we may not use it. And I know what you think. Oh, God, independent fault alarm. That's not going to work. Oh, God. So let's add persistence before somebody is really leaving the room. It's this. We just take the message bus, the message queue, rename it to event bus, and put a persisted log on it. Maybe it's a write-ahead log, maybe it's a key value store. Remember, with the event bus, we have basically established ordering. We put some sequence numbers on them. So it really doesn't matter how we write them, as long as at the end of the request, everything is persisted. It's pretty easy stuff, really. Then you have to figure out, obviously, how fast the guarantees they provide. It's okay. So, but what about the availability? At this point in time, we could run this theoretically on one machine. And you know what they say about one machine? It can burn. So we need to talk about availability because we don't want to go down. But more than one machine means it's kind of something. So let's talk about TCP. Amazing protocol. It's the backbone of the internet. Reliability, flow control, congestion control, all things you need for a real network in the real world with copper wires in Germany in the ground. No fiber for us, only copper. So packets get lost, so TCP has some reliability mechanisms built in. But these come at a cost. The constant hacking. You have to acknowledge everything. Every message there is will be acknowledged. And the reception will be acknowledged as well. So that brings a lot of chatter on the network that you may not want, especially if you want to be fast. So maybe we look into UDP, the unreliable protocol, the one that doesn't have a connection, but just sends messages. It's like screaming into the void. This is, by the way, also the phase of people that never used UDP, like, oh my God, you can't use this. This is horrible. What if the message gets lost? So, but it's not so bad because remember, we have sequence numbers. So everything is continuously sequenced. So you have a 1, 2, 3, 4. And if you send these messages to some receiver, you can basically check. You can like 1, 2, and then you get 4, and you're like, wait a moment. I expected 3, not 4. Now I'm at 4? No, there's a 3 missing. So we can basically implement our own protocol that says, okay, we process one by one, and then if we miss some, go back and say, hey, I didn't get 3. Give me 3 again. Something happened on the way. And we basically have a very optimistic product suddenly. Okay. But why do we do this? Like, yeah, okay, we don't want to use TCP and the hacking is a bit annoying, but we have great cables these days. It's okay. It's called multicast. Who knows multicast? More than I expected. Why don't you use it? So, what's multicast? Multicast is this great concept that you can do in connectionless system, where you basically send something, and then your friend, the switch, replicates your message. You send it to a broadcast group, to a multicast group, and your cool friend, the switch, takes the message and replicates it in hardware and sends it to everybody that's subscribed to the multicast group, which is pretty cool, because then you don't have to know all the recipients, you just have one group, the recipients join this group, and this little fella does the replication. And because it's hardware, it's pretty fast, actually. Modern switches can have specialized hardware to basically have routing tables for this, so they know already the recipients when you send messages to a multicast group. Okay, that's pretty cool. More boxes, am I right? We are going to change some things up. We have a WebSocket still, that's a given. But we don't have the event bus anymore, it's gone. We're going to introduce this sequencer. The sequencer has this job. It takes a message, puts a number on it, and then uses multicast to send it to multiple matching engines. We're going to run multiple ones. Remember that we built the system as a state machine. So same input, same output. This is pretty interesting. So basically, you can send, as long as you send all messages to all matching engines, they will arrive at the same end result, really, and emit the same messages. So you take the sequencer, you use your friend, the multicast, and send the message to the multicast group, which all 3 matching engines joined, and the matching engines process their request, come to a result, and send it to what is then called the publisher. What does the publisher do? Well, it takes all these 3 messages from these 3 matching engines, and it compares them, and checks, do they all come to the same result? Or is somebody really like, what? What's going on? No, it's 5, right? You want something verifying this so that you have basically agreement on all matching engines. Because if one disagrees, something's wrong with the system. From the publisher on, we are going to persist the logs. So you get the messages and you persist them, so you still have your auditability solved. Okay. But what if it crashes? I mean, a matching engine can go down, right? Well, we're going to do this. In case a matching engine crashes, we're going to boot a new matching engine. In this case, let's say the first one crashed, matching engine 1, and it starts listening to the multicast group, so it gets all the messages coming in, and then it just asks matching engine 2, hey, give me your state, last thing you processed, the sequence number, where you left off, give it to me, I'm going to put it in my memory, and then I'm going to just apply the events that were missed in the meantime, and I'm up and running again. So we significantly reduce the downtime in case of a matching engine failure in the end. And so we basically solved availability. Yes, there are still some things that can go down, but they hold so little state that it's very easy and fast to redeploy them instantly. With a backup, obviously. So, the learnings. You may not need a database. Reduce the fallout in case something goes wrong. And last one, a state machine can save the day. So yeah, that's it. And cool thing, like the slides you can find on the left, stage left, I don't know, the left one. And you can go to rex.timkechele.me and you have a fully operational version of it with a React front end that is not up to the task of any front end developer. And you can enter your own price and quantity and do some paper trades. And that's basically it. Thank you very much. And I hope you learned something.